Hi guys, welcome to today's tutorial. In this tutorial, we are solving related race questions together. And as you can see, I have a question here selected from the worksheet 6. When solving related race questions, drawing the diagram is very important because it allows you to see the problem very clearly, and we can also convert those information in the real life into mathematical symbols and make use of the formulas. So let's see what we have here. We have a baseball diamond, which is a square, and we also know that its length is 90 feet long. So let's just draw this first. Diamond, square. Okay. Drawing a square could be difficult, so let's try my best. Okay, so we know that it's 90 feet long. It's 90 here. And what we know, it's the picture is at the center of this square. So the picture is kind of here, right? And throws a ball at 90 miles per hour. The speed is given. So let's say he's throwing a ball in this kind of direction, right? And we also know how fast the distance between the pitcher and the ball is changing, right? The rate of change is 90 miles per hour, right? Is the ball, just throw out the ball in this way. And what we are asked is the rate of change, right, of the distance between the first base and the ball. So assume that the ball is here. The first base is right here, right? So we need to find out the distance, right? Of the first ball, I want to draw a straight line. So as you can see, the red line here is the distance between the first base and the ball, right? And the blue line there, the length of the blue line is the distance between the pitcher. Let me highlight that here. The pitcher is at the center, right? The blue line is the distance between the pitcher and the ball, right? And we also need to find out the original distance between the pitcher and the first base. So we have a kind of a right triangle here, which will allow us to establish some kind of formula later, right? So let's assume the distance between the pitcher and the ball is x. So we're assuming that the length of that blue line is x, and also we assume that the distance between the ball and the first base is y, right? So let's find out what we've known here. We've known that the rate of change of the blue line is 90 miles per hour, right? But you know the baseball diamond is given by 90 feet, so we need to convert that kind of unit into either feet or miles, right? But the note here says that 1 miles per hour is equal to 22 divided by 15 feet per second. So we'd better just convert the 90 miles per hour into feet per second. So 90 miles per hour, right, is equal to 90 times this 22 divided by 15 feet per second, right? Which is, if you calculate this, you get that this is 132 feet per second, right? So what we have known here is the rate of change of x, which is dx dt, is equal to 132. And we want to find dy dt. Right? Want to find dy dt. How do we do that? Let's just find out the relation between x and y. As you can see that y is the hypotenuse of this right triangle and x is the length of one side. So if we figure out the length of that purple side here, we will be able to establish a equation of x and y by the Pythagorean theorem. So let's figure this out. Since we know that the length of the x square is 90 feet, so we can divide 90 feet by square root of 2 to figure out the length of this side, because if you draw a line here, you will see that in this small right triangle here, this angle has 45 degrees, right? So it's a special triangle. And for this kind of triangle, we know that the ratio of the length of the side and the length of the hypotenuse is 1 to square root of 2, right? So let me give you this information here. For a right triangle like this shape, 45 degrees, right? The ratio of the length of the side is 1 to square root of 2. Right? So it means that we can just divide the 90 feet by square root of 2 to figure out the length of the side z. Okay, so we have z here equal to 90 divided by square root of 2, which is equal to 45 times square root of 2 feet. Okay, z is equal to that. Let's just ignore the unit for a second, because we're gonna compute this. We don't have to use the unit right now. We can state that in our conclusion just for convenience. Okay, so we know that z is equal to this, right? So by the Pythagorean theorem, we can establish the relation between x and y. So we have x squared plus y squared, plus z squared equal to y squared, right? Which gives us that x squared plus this 45 square root of 2 squared is equal to y squared. So from here we know that if x is given, we can figure out y, right? If y is given, we can figure out x, right? So that is what we have for the relation between x and y. So what the question is asking, it's the rate of change of the length of the hypotenuse, which is dy dt, when x is equal to when x is equal to 90 divided by square root of 2, because it says that when the ball crosses the home plate. So after the pitcher threw the ball, the length of x will be increasing, right? And by the time the ball crosses the home plate, then the ball will be here, right? So that we know that at this time, x will be the same as z, right? As log. So x will be 45 times square root of 2, which is just 90 divided by square root of 2. So we want to find dy dt when x is equal to 90 divided by square root of 2. So that is what we were looking for. Okay, so from what we had just now, that equation, we can take the derivative with respect to t to figure out the relation between dx dt and dy dt. So let's apply our implicit differentiation to figure that out. We take the derivative d over dt of the left side here, as well as the right side. Okay, so that we have apply the chain rule, right? So it's 2x times dx dt. Okay, hope that you're familiar with this implicit differentiation. If not, can go back to review this because everything is based on implicit differentiation, and we also know that implicit differentiation is based on chain rule, so everything is built up step by step. So that is the derivative of the first term. For the second term is 0, right? So write 0 here. If you don't write 0, it doesn't matter. I just want to remind you that this derivative of this constant is 0. And for the right hand side, we have 2y times dy over dt, right? So this gives you the relation between dx dt and dy dt. Right. Cancel out this 2. Right. Notice that we're looking for dy dt, so we should solve for dy dt. Right. So dy over dt is equal to we divided both sides by y, so y will go to the other side, so it's equal to s over y times dx dt, which means that if we know x and we know y and we know dx over dt, we will know dy over dt, right? So let's find out all these things on the right hand side. We have known that x is equal to 90 over square root of 2, which is 45 square root of 2, right? By the assumption, right? And at that time, we can find out t, right? By this relation here. So plug in x equal to this into this equation, we will be able to find what y is, right? So y will be equal to y squared first, equal to 45 square root of 2 squared plus 45 square root of 2 squared, right? And it gives you that y is equal to, actually just, 90 at this time, right? Because you can see that if x increases to this length, then y will be the same as the side, one of the side of the square. So no need to compute, y is equal to 90. If you compute that, it's fine, but I'm just telling you that it's 90 feet without computation, right? So we know that y is 90. And we also know dx over dt, which is already given. That is the speed of the ball, and it's also the rate of change of x, right, which is constant. It does not change. It's given by constant speed, which is 90 miles per hour, and we have converted this data into 132 feet per second. So we're just using 102 feet per second, right? dx over dt, 132 here. So if we plug in everything here to have x is equal to 45 square root of 2, y is equal to 90, this is equal to 132. So everything together suggests that this will be 132 divided by square root of 2, which is just 66 square root of 2, right? So now we can draw our conclusion. Therefore, the distance, it's increasing at a rate of 66 square root of 2 feet per second, right? So note that this conclusion is very important because all we had was just a mathematical computation, just symbols, right? And we need to turn this information back into the information in our real life. If you don't give this conclusion, we don't know what does that mean by 66 square root of 2. That means 66 square root of 2 feet per second, right? And we also know that the distance is increasing, not decreasing, because it's a positive number. So what I'm saying is giving the conclusion is important. If you don't give the conclusion, you will be taken some marks off. So just keep that in mind. That's for the completeness of the answer, right? So that now we have completed this question. Okay, so that is our question 3. Let me just summarize a little bit. When we see a related rate question, we firstly draw the diagram. Let us see clearly what does that mean in the real life. And we convert those information in the real life into mathematical informations. And we find out what we've known, right? And we find out what we need to find. In this case, we've known dx over dt. What we need to find is dy over dt, so keep that in mind. And since this is related rate questions, so we need to establish the relation between x and y by using the information in our diagram. And in this case, the relation is established by using the Pythagorean theorem, by using the right triangle, right? So, so we know that once we figure out the y, once we figure out the x, we will be able to figure out the y. And the question asks you the rate of change of that distance, dy over dt, when x is equal to 90 over square root of 2, right? That's need to be found out by yourself, because the question just said that when the ball crosses the home plate. What does that mean? That means x is at here. The ball is at here. So x will extend all the way to the bottom like this, right? So x will be equal to 90 over square root of 2. So we need to find out all these detailed information and put them back into the equation. And in the middle, we of course need implicit differentiation to work this out. So make sure to review this stuff before attempting the related rates questions. And at last, after solving everything, don't forget to give the conclusion, because we need completeness for the answer. Okay, so that is question 3. Now let's take a look at the next question here, question 4. What we have is an inverted canonical tank which has a height of 6 meters and a diameter of 4 meters. So it's a container of the cone shape and also upside down. So let's draw it here. cone which is upside down. So it's like that. It has diameter of 4 meters, right? And the height here 6 meters. If we look at this at a two-dimensional picture, then it's like that, a triangle. And we know that is radius is 4, diameter is 4, right? So the radius is 2. Notice that later on we're gonna use the centimeters, right? So it's better to just convert the meters into centimeters, right? So 6 meters is equal to 600 centimeters, right? And 4 meters is equal to 400 centimeters. So in our two-dimensional picture, we have that the canonical tank has radius 200 centimeters and the height 600 centimeters. Okay. What we also know is the water inside this container is leaking out. So assume that we have some volume of water inside. The purple line here represents the water level, right? So you see that as the water is leaking out, the level of the water will be decreasing, right? It's going down the level. So what we want to find out is how fast is the depth changing when the height is 3 meters. That means when the height is 300 centimeters, right? So let's write out what we know here is dv dt, right, which is equal to 10,000, right? But since the water is leaking out, so the volume is decreasing, so it should be negative 10,000. Right? That's how fast the volume of the water is changing based on the information we know here. But how is that related to the depth of the water? What is the depth of the water? The depth of the water is the length of this, this green line here. You see this green line, right? That's the depth of this water. Let's set that to h, right? And also set the radius of the water to be r, right? Set this to be r. So since the shape of the water is also in the cone shape, so we can use the volume of the cone formula to find out its relation by using R and H. So we know that the volume of the water, V, it's equal to 1/3 times pi r squared times H. So by this thing, we can find out the relation between the volume and R and H. But still, we have 3 variables here, which are V and R and H. In our related rate questions, we normally just have 2. So it seems that we need to eliminate one of the variables here. Right? How can we eliminate one of the variables here? If we look at the two-dimensional picture, you see this similar triangles here. Let's say that this is a small triangle 1 inside this large triangle, which I am highlighting by this red line here. So this red triangle is a large triangle, right? So triangle 1, it's similar to the triangle 2, which means that the corresponding length of sides, right? The length of, the ratio of the corresponding sides, they are the same. So, so I can write R over 200, right? That is the length of this side of this small triangle over the length of the side of the large triangle, equal to the height of the small triangle, which is h, right, over the height of the large triangle, that is 600. And by using this information, we can find out the relation between the variable r and h, right? And then we will substitute this into the volume equation so that we can eliminate one of the variables. But now, which variable should we eliminate? Should we eliminate h or should we eliminate r? So notice that the question here is asking us the rate of change of the depth, right? That means we are looking for dH over dt, right? So we want to find out the relationship between h and r, right? So we cannot eliminate h because you need to use it. So we need to eliminate r, right? So eliminate r, which means that we should represent r by using h. So r is equal to 1/3 of h, right? And we plug this back into the volume equation, right? So we have v equal to 1/3 pi r squared, which r is this thing squared, h, right? And we simplified because we are gonna use it, right? So it's 1/9 h squared times h. And finally we have 1/27 pi h to the third. This is the volume, right? After having this, that is the relationship between the volume and the height, or you say the depth. Then we're gonna take the derivative on both sides with respect to the time t. Okay, so take the derivative, we have dv over dt equal to 1/27 pi, constant, factor this out. This is times 3h squared times dh dt by using the chain rule, right? And then we kind of simplify it, but it's fine if we don't. Okay, so we are looking for this guy here, dh dt, right? When h is 3 meters, right? So we can just plug in h equal to 3 meters, which is just 300 centimeters, right? And we have known dv over dt, so plug in everything here, we should be able to find dh dt, right? So let's write that out here. It's dh dt. It's equal to, if we cancel this out, we have 9 here, right? So it's dv over dt times this is pi over 9, so it will be pi over 9 over pi if we flip that to the other side, times 1/h squared. Okay, and then we plug in everything right now. dv dt is equal to negative 10,000, right, times 9 over pi, right. H is equal to 3 meters, right, which is 300 centimeters, using centimeters right now. Okay, so that is equal to negative 10,000 times 9 over pi. This is 90,000. And we cancel this out, right? And also this 10,000 cancel with the 10,000. We have a negative sign left. So it's negative 1 over pi, right? That is our the rate of change of the height, right? dh dt. We found this. Now let's just make the conclusion. Therefore, the height is decreasing since it's negative, right? So it's decreasing at the rate of 1 over pi centimeters per second. Okay, so that is the conclusion. So if we compare this question to the previous question, we have one more step, which is eliminating the one of the variables here, right? And also we need to make use of the similar triangles. But you see that the process is basically the same. You use the diagram, the setup, and then use some formula to establish the relation between two variables. In this case, it's v and h. And then after that, you differentiate both sides with respect to t to find out the relation between dv dt and dh dt. We know that we've known dv dt at the beginning, and we're looking for dh dt. So our goal was very clear. We're looking for this, and then we know that we need to find h, right, and dv dt to find out dh dt. And at last, when we're done, we draw the conclusion. And that is the answer for question 4. So that's it for today. If you like my videos, make sure to subscribe to my channel. I'll make more videos about that in the future. So see you guys in the next episode.